Alright guys, so today we're going to talk about parametric equations. So what is a parametric equation? Let's start with that. Well, we're going to talk about parametric equations as equations that depend on a certain parameter. So let's think about cosine of t, for example. Well, that would be your x-coordinate depending on a parameter that you can think about more or less like a time variable. Now, if we would say, well, y is equal to sine of t, this is a very, very typical equation that we can write in parametric form. And what that's going to happen is we're saying the position of a particle, so to speak, the x-coordinate of it depends on a parameter time in terms of the cosine, or as a function of the cosine, if you will. And similarly, the y-coordinate depends on t as a function of time as the sine of t. Now, what would that represent? Well, that represents, you know, what the sine and the cosine look like. They oscillate. But what would it look on the plane? So if you were to take out that time dependence. So let's try to go ahead to look at the graph. And I started with the first one, which is probably the worst one I draw, which is going to end up being a circle. But I'll show you how you would draw the graph. So let's start with that. So at times equals 0. So you have to make a table. I'm going to put it here to see if we have enough space. So I'm going to put t here. I guess I'm going to need an extra column here. How about that? X and y. Good enough. So let's start at times equals 0. The x-coordinate is going to be the cosine of 0. Cosine of 0 is 1. So we get in at times equals 0, the x-coordinate is going to be equal to 1. At times equals 0, the sine coordinate is going to be the y-coordinate, is going to be the sine of 0, which is 0. So what that tells me is that my first point, this one right here, is going to be the point 1, 0. But this graph is going to look just as a graph on the plane, but it has more information. This is telling me that at times equals 0, the particle was located there, if you want to think about it in terms of particles. Now let's go ahead and look at one that will be somewhat easy to evaluate. We know, for example, pi over 3. Why? Because we want to use the unit circle. It's going to be the unit circle, hint, hint. So the cosine, and why? Because you see, the point in the unit circle are the form x cosine of the angle, and the y coordinates are y sine of the angle. So it's a very familiar first example. All right, so I plug cosine of pi over 3. Pi over 3? I wanted pi over 6. I went all the way here, which is okay. Sure, let's draw this one. So cosine is going to be 1/2, and the sine is going to be square root of 3 over 2. And so your x-coordinate is going to be more or less about 1/2. And by the way, I should have labeled this point right here. We should have labeled it as 1, 0. Now I'm going to go to the next point. I'm going to keep this color. It's going to be 1/2 for the x. And I'm going to be square root of 3 over 2, which is, I'm just trying to continue around the unit circle because I know what the graph will look like. But you would plot it, and you would get that point to be times equals pi over 3. And you would have the x-coordinate would be 1/2 and then square root of 3 over 2. Now you can see how if I would have put pi over 6, I would have ended up with a point over here. I didn't, but the point is you're going to be making a table because these are going to be a little bit harder to draw than the graphs that you already know how to draw. So pi over 2, cosine of pi over 2 is 0, sine of pi over 2 is 1, and I'm going to end up at this point here, roughly there. And I'm going to do a couple more just because, and then we're going to draw the graph, which is going to be the unit circle. So let's do, for example, 2 pi over 3. Now that we started with the pi over 3, is why not? And so 2 pi over 3, the cosine is going to be your negative 1/2. But your sine is going to be still square root of 3 over 2. Just evaluating all the points. So this should be more or less here. And you can imagine the next one's going to be here, and so forth and so on. And if I continue drawing, by the way, parametric equations, you could have, you know what? Let's stop right there. Parametric equations, you can determine that the parameter, for example, can go from 0 all the way to pi. Oh, look at that. Then my table is complete just by doing this. Good on me. So So you see, you can pick the values of t when your parametric equation will be defined. So why is that? Well, think about it that you may be interested in a phenomenon only between a certain amount of time. So depending on what you're trying to model, that may actually be a restricted or a closed interval in this case. Of course, I could have said also from times from 0 to infinity, and then this would have just kept going around and around and around. By the way, I should probably also label all my times here. So pi over 2, and then so forth and so on. So we said this one was 2 pi over 3 times equals 2 pi over 3, and so forth and so on. All right, so that's our first example. So that's going to be pretty much how we're going to be graphing parametric equations. We're going to make a table, we're going to plot points, and then we're going to notice another thing, by the way, I almost missed this point, is that the graph of a parametric equation, the time parameter gives you more information than just this graph, because it tells you how the graph is formed or in what direction it's going. Because at times equals 0, you are here, times equals pi over 3, pi over 2 to pi over 3, so you're going in this direction. So parametric equations, by virtue of having a time associated to them, and I'm going to keep calling it time because that's really the most logical value for t, or what we should be considering it like, that also gives you a direction for the curve. So we end up with the parametric equations, and I should have said parametric equations to a curve or for a curve. All right, so that's that. We're gonna graph one more, and then I'm gonna show you how you can remove the parameter. In fact, let's remove the parameter from this one. So this is the parametric equation of the curve. We can also transform it into what we're called the rectangular equations, or the equations in the Euclidean plane. So let's take a look at that. Let me erase a little bit here, and I can fit it right there. All right, so the trick is to find some sort of equation by which I can relate this coordinate, and I'll remind you of the one that is the right choice, which is going to be the cosine square of t plus sine square of t equals 1. Ooh, t equals 1. Can I fit the 1? Yes, barely. All right, so if I plug that in, well, that what corresponds to is going to be x squared, plugging x equals cosine of t, and y squared, plugging y equals sine of t, equals 1. And that gives me the equation of the unit circle. That gives me one equation, or the equation for this curve. However, in this particular case, it's a little bit harder to describe, because I'm saying, well, x now is going to be between -1 and 1, and y is going to be between 0 and y. Well, this restriction was much easier. So parametric equations have their use, and there's times when they're going to be way more convenient to turn things into parametric equations. All right, let's do another example, and then I'm gonna graph the equation, and I'm also going to eliminate the parameter in that other one. All right, so let me erase. I'll be right back. All right, so let's take a look at this one. By the way, I put this a little bit close there. Should have probably put some sort of bracket or something. So let's grab those two equations, with the time parameter will be between 0 and 2. And let's see what it looks like. So as we did before, we're going to do a little table. Let me put it here. Can I fit most of it? Yep. Again, time t. I want to start at 0 because that's my endpoint. And I'm going to do a 1/2. Then I'm going to do a 1. 3/2, but I don't think I can fit it. Yeah, I'm pretty much out. And I'm going to put a 2. I don't think you're going to be able to see that one. We're going to evaluate it and put it on the graph. So let's go ahead and put our graph here. And see what we get. At times equals 0, x is going to be 0 times 2, 0 minus 1 is going to be -1. So my x coordinate is going to be -1. Let's evaluate the y coordinate. At times equals 0, this is going to be 0 plus 1 is going to be 1. So my point is going to be from -1 in the x, put it here, and 1 in the y is going to be this point right here. It's going to be closed. Why? Because I have that times going to be between 0 and 2 equal. So if this would be, for example, strict, and I would make an open point. Okay? All right, so at 1/2, when I multiply here times 1/2, I'm going to have 1/2 times 2 is 1, minus 1, x is 0. Now I'm going to have here 1/2 is going to be 1/2 squared is going to be 1/4 plus 1. That's going to be 4/4, 1/4, and plus 4/4 is going to be 5/4. All right, this is going to be very technical and drawn to scale, as you can imagine. So I'm going to go to 2 here, divide by 2, divide by 2. So roughly here I'm going to have 5/4. 0, 5/4. Very technical, right? Yeah. All right. At 1, I get 2 times 1, 2, minus 1, 1. And at 1, I get 2 there when I evaluate 1 squared plus 1. 1 plus 1 is 2. So I'm going to be going to 1, 2. So 1 here, 2 here. So roughly there, it's starting to look a little bit like a parabola. And I want to look at what happens at times equals 2. I get 2 times 2, 4, minus 1, 3. That's for the x. And then for the y, it's going to be 2 squared plus 1, so 5. 3, 5. So if this is 1, this is 2. Roughly here it's going to be 3. Sorry about that graph. And then I'm going to go all the way to 5. You see that's going to be a parabola. So it's going to be going out in this direction. I'm going to fail here because I will not be able to draw that point. But you see how I'm going to have to cap that off there. All right, and of course this point 3, 5 is going to be closed because it is going to be included because that's going to be equal. All right, so now there's another thing that we can do. We can eliminate the parameter. That's going to be the next thing I'm going to do. But there's also another thing that we can do. The parameter may also be changed. So I can also reparameterize my equation. So for example, so I'm going to do that first maybe. So what I can say is if I would like to speed up the velocity, by the way, this graph is going in this direction as we said, but let's say I want it to go faster. So I'm going to change my parameter. So instead of doing t, I'm going to do times is going to be 2 times s. So every time I increase s by 1, t will be increased by a factor of 2. So it's going to be, so my parameter s, it'll require less changes to make this change more. I'm being a little bit sketchy there, but let's say I'm just reparameterizing by a factor of 2. All right, so if I plug that in, what do I get? Well, I get that x now is going to be equal to 2 times 2s minus 1. So x is going to be equal to 4s minus 1. And y is going to be equal, when I plug it in there, I'm going to have 2s squared. Let me just write it. Sorry about that. I'm skipping a little bit there. But what I want to make sure that we agree on is the following. That if t is going to be equal to 2s here, oops, wrong marker. That one is almost invisible. But if I'm going to use 2s here, then when I look at this inequality, I divide by 2, I get that my equations are satisfied for s between 0 and 1. So my reparameterization, I also have to be mindful of my parameter. So I'm going to put it here that 0 has to be less or equal than s and less or equal than 1 when I solve that inequality. So that's one thing you can do. You can reparameterize, changing the speed, so to speak, of the curve, and then it's going to give you different equations, but you have to change your intervals as well, so you can end up with the same curve anyways. All right, let me eliminate the parameter from this one. This video is probably getting a little bit too long, so I'm going to go ahead and eliminate the parameter. I'm going to erase everything, leave it just here, and I'm going to eliminate the parameter, and then we'll finish the video right there. I'm going to erase. I'll be right back. All right, so we're going to try to eliminate the parameter here. So what do I do? Well, the easiest way is to look for which equation is the easier to solve for t in terms of the other variables. So look at this one. This is linear. This is quadratic. I really don't want to deal with that one. So I'm going to do the linear. I'm going to solve for t in this equation. So I'm going to add 1 on both sides. I'm going to have x plus 1 is going to be equal to 2t. I'm going to divide by 2 on both sides, and I get that t is going to be x plus 1 over 2. So I'm going to plug that, let's call it equation, call this one 1 and call this one 2. So I'm going to grab equation 2 and I'm going to plug it into 1. 2 into 1. So whenever I see a t, I'm going to plug that expression. So I get y is equal to x plus 1 over 2 squared plus 1. Now this one is pretty nice in this form. Perhaps the only thing we could do is FOIL it out and write this as x squared plus 2x plus 1 over 4 plus 1. You could do a common denominator if you wanted and write this as y equals to 1/4 of x squared plus 2x plus 1 plus 4 is plus 5. You could do that. If you're in my class, you're probably good leaving it here. But some other people may want you to go a little bit further. No big deal there. And that's how you eliminate a parameter. Is it always going to be possible to eliminate a parameter? Nope. Are we going to give you ones that are very likely that you can solve? Yes. The other thing that can happen is you may need some trigonometric identities to deal with it, or some clever tricks. But the idea is more or less the same. Now I see that my 2 into 1 didn't fit. Oh well. Alright, so we're going to stop there. I think that's a good video, a good point to stop. Thank you for watching, and I'll see you in the next one.